All right, good afternoon. So Tobias, how'd your ball game go?
Good, we won.
Good. Who'd you play?
Red Valley.
All right. Phew. Sorry.
Bless you.
Thank you. All right, so let's see. I hadn't heard from Weston, but he's been sick all week. I hope he's doing better. Let's see. Is Jada there?
She's coming.
Okay, thank you. All right, so Tobias, did you get my message about yesterday? Yeah? Okay. All right. Well, so our plan is today is to go over 9.4, and then I don't know if we'll have time for 9.5 or not, but I was hoping we'd get to 9.4. Oops. Oh, hold up a second. All right, there's Jada. Okay. So let's go ahead and get started here. Okay, so 9.4, I'm relatively certain we're not going to have any trouble finishing this section today. And 9.5 is such a short lesson, we can do it in 10 or 15 minutes. I just don't know if we're going to have time today to do two or what, but we'll just see how it goes. 9.4 is kind of an interesting section here in that the math is actually very easy. It's pretty much algebra 1 type math. What's difficult about this section is all the vocabulary and just keeping it straight. So hopefully, I think the guided notes are going to be huge for you in understanding this lesson, because without the guided notes, I've tried to teach it and it gets to be a jumbled mess for the students. So hopefully it's like I say, it's really the vocabulary. Okay. So the title is Graphical Solutions of Autonomous Equations. See, right there from the beginning, you don't even know what an autonomous equation is. So we've got to kind of teach it from the ground up here. All right, so a differential equation for which dy dx is a function of y only is called an autonomous differential equation. Okay? So it's a function of y only. So like where we've dealt with, our first derivatives were functions of x. And then we've had functions of x and y, where we've had x's and y's in the derivative. Okay? So now if our derivative just has y's in it and no x's, then that's an autonomous differential equation. And so that's going to be our focus here today. Okay? All right, so for example, if we go through and we take the derivative of this, all right? So the derivative of 1/5 of a natural log, you bring the 1/5 down, and then the derivative of the natural log of blob is 1 over blob times the derivative of blob. So the derivative of the natural log of 5y minus 15 is 1 over 5y minus 15 times the derivative of 5y minus 15, which is 5 dy dx. Because the derivative of 5y is just 5, but you have to multiply by the dy dx whenever you're taking the derivative of y. Okay, then the derivative of negative 15 is 0, the derivative of x is 1, the derivative of 1 is 0. And so now when we solve this for dy dx, you might actually see, even as early as this, that there are no x's in here. There's just a y. Okay? So when we solve this, I'm going to just simplify the 5 and the 1/5, then multiply each side by 5y minus 15. So then when we get the dy dx by itself, we just have a function in y. There's no x's here. So if there's a function just in y, then that is an autonomous differential equation. All right? All right, so go ahead and try practice 0. And by the way, just so you understand my numbering on this is, if ever I do a practice 0 or like the next one, 0.5, it means there's no examples like that even in your book, okay? And so just kind of based on what I thought students, I felt like that we needed some more examples before we get into what the book is doing, okay? So this is not really, there's not an example of it in the book. So that's why I do example 0 and then practice 0. All right, so Jada, what do you think? Yes or no?
Yes.
You are correct. So when we take the derivative of y squared, it's 2y dy dx. And then the derivative of 5x is just 5. And see, then when we solve for dy dx, see there's no x's here. So it's an equation just in y, so the answer is yes. All right. Any questions on that? Okay. All right, next, an equilibrium value. So equilibrium values are those at which the derivative, dy dx, equals 0. Okay? So says if dy dx is a function of y, so if we have an autonomous differential equation, then the values for which dy dx equals 0 are called equilibrium values or rest points. Sometimes they use either terminology. And the way that I kind of remember that is I think of like a seesaw as being in equilibrium when it balances or when it's at rest. So an equilibrium value or rest point. It's when everything is balanced. All right, so find the equilibrium value for dy dx equals 5y minus 15. So let's see if you can do that. All right, so Tobias, what do you have?
So would you take the derivative?
No, it's already the derivative.
Oh, yeah.
So the equilibrium value is where the derivative is equal to 0.
So you just plug in for y?
So what value for y would make that go to 0?
3.
3. So that's the equilibrium value.
Oh.
So you can set it equal to 0 and solve. So y equals 3. That's your equilibrium value. So it's where the derivative is equal to 0. So you're not plugging in 0 for y, you're setting it equal to 0. Okay? All right, next, phase lines. Phase lines are used to construct sign charts for y prime and y double prime. We plot on the number line the equilibrium points. Okay? So this is draw a phase line for the equation dy dx equals y plus 1 times y minus 2. All right, so now this is already factored, so that's great. So if we think what would make this go to 0, it would be when you set each factor equal to 0 and solve. So it'd be -1 and +2. So those -1 and +2 are our equilibrium values. So you can have more than one, however many factors that you have. Okay, now you might remember that we did this in Calc 1. Okay, not when it wasn't a function of y, but when it was a function of x, where we called them, instead of equilibrium values, we called them critical values or critical points. It's the same idea. It's just now it's when they're a function of y. We call them equilibrium values. So we put those on the number line. So -1 and 2. And so this is called a phase line when the function's in terms of y. So now we do the sign chart, just like we did back in chapter 4 of Calc 1, where we pick a number in each interval and plug it in to the derivative. And you just see if it's positive or negative. We don't really care what the number is. So we pick a number to the left of -1. Let's say -10. And you plug it into the derivative. So -10 plus 1 is negative. -10 minus 2 is negative. Negative times a negative is positive. All right, then we pick a number between -1 and 0. -1 and 2. Let's say 0. So we plug it into the derivative. 0 plus 1 is positive. 0 minus 2 is negative. Positive times a negative is negative. All right, then we do a number bigger than 2. Let's say 5. 5 plus 1 is positive. 5 minus 2 is positive. Positive times a positive is positive. Okay? So that's like the sign chart we did for Calc 1, the first derivative test. All right? So any questions to this point? All right, now there's a new chart that I want you to draw on your paper, like somewhere near practice 1, okay? Or in that. And this, it seems like a little simple chart, but it's going to be important. So put in the little box, put plus. Next to a plus, put an arrow to the right. And next to a minus, an arrow going to the left. All right, so now what we'll do is we'll draw these little arrows on the phase line. So see where this area is plus, then we're going to put a little arrow here going to the right. And where this one is a minus, we're going to draw an arrow to the left. And then where this one is plus, we're going to draw an arrow to the right. All right, now, the number where if both arrows come at it from the same direction, this is called a stable equilibrium value. And where the arrows are going away from the number, this is called an unstable equilibrium value. Okay, so that's new. The arrows, and then again, where the arrows are coming together, stable. Where they're going apart, that's an unstable equilibrium value. Okay, so for practice 1, first you need to factor that and identify the equilibrium values. Okay, then put them on the phase line and make the sign chart. Then once you do the sign chart, you do the little arrows. Then you figure out at each point, is it stable or unstable? All right, so see if you can do that for practice 1. All right, so Tobias, what are the equilibrium values?
I got -2 and 2.
-2 and 2. Okay. All right. Let's see. I guess I should. All right. So for the phase line, you graph the -2 and 2. All right. So did you both get plus, minus, plus?
Yep.
Okay. And then, so that means you have a right arrow, a left arrow, and a right arrow. Okay. We good with that? Okay. So then, Jada, which one is stable? Which one is unstable?
The -2 is stable and where the 2 is unstable.
That's right. All right. Very good. All right. Any questions on that? Okay. All right, next. Derivatives and graphs. Okay, now this again is going back to chapter 4 in Calc 1. So this is nothing new. I'm just kind of reminding you of it. So where the first derivative is positive, the graph is increasing. Where the first derivative is negative, the graph is decreasing. Where the derivative changes sign, that's where you have a local max or a min. Where the second derivative is positive, let's see. Where the second derivative is positive, that's where the graph is concave up. Where the second derivative is negative, that's where the graph is concave down. And where the second derivative changes sign, that's where you have a point of inflection. Okay? All right. So when we did the first derivative test, when you plug into the first derivative where it's positive, that's where the graph is increasing. It's going up. If this first derivative test yields a negative value, that's where the graph is decreasing. So where it changes sign here, where the first derivative is 0, see here, that's where you have your local max and min. And so if it's going positive, 0, negative, then that would actually be a max. All right, where the second derivative is positive, that's concave up. Where the second derivative is negative, if you do the sign chart and you get a negative, that's concave down. And so then where the graph changes concavity, that's a point of inflection or inflection point. All right, so see if you can do practice 2. Now, that's the same graph that you did for practice 1. So that might help you because you've already taken the first derivative. Okay? Or have you? Did we take? No, we already have the first derivative. But for the point of inflection, you're going to have to look at the second derivative. But it's the same graph that you had in practice 1, if that helps. Okay, now, I know you probably haven't had time to finish, but here's the deal, is that the second derivative is a little tricky. So I'm just curious, before you go too far, if you got the second derivative right. All right, so can either one of you, so if this is the first derivative, what's the second derivative? Jada, what do you think?
2y.
All right. That's probably what I would have thought as a student, because, and the reason I say that is because when I did these, I made the same mistake that you just did. All right. Tobias, do you know what mistakes you made?
I'm not sure, but I feel like, I don't know. I think I might. Well, I might not know, but I don't know. I think I know why it's
What do
wrong.
you think it is? What
Well,
do you think it is?
in my head, when it says dy dx equals y squared minus 4, and you're finding the double prime of y, that just confuses me because there's like the y is in the equation, it's not an x like before, where usually it's y equals x, and then you find the double prime of that.
Right.
But the y is in the equation, so like that just throws me off.
Yeah. So we did those in we call those called implicit differentiation, when it's not y equals in terms of x. But when you have y's in the function, when you take the derivative, it's 2y dy dx. And that's the part that you missed, Jada. That's the part that I missed as a student. That's the part that everybody misses. See, when you take the derivative of x squared, it's just 2x. But when you take the derivative of y squared, it's 2y dy dx. And the reason is because, see, because you're taking the derivative with respect to x. So let's just say, so if I had, let's say y equals x squared, then y prime is 2x, and then you can think of it as dx dx. But when you take if you have, well, let's do it this way. Let's write it as dy dx here from the beginning. So here, if this is the first derivative, dy dx equals 2x, then then when you take the second derivative, you can write it as y double prime, or let's do it like that. Okay, but if the original function is in terms of y, if dy dx equals y squared, then when you take the derivative, it's got to be 2y dy dx. So you have to throw in that extra little part. So then how did I go from here to here?
You plugged in what it gave you for dy dx.
That's right. So this is dy dx is y squared minus 4, or y plus 2y minus 2. And so now when I do my, when I graph my phase line, I'm going to have 3 points. Okay? So what are the zeros here?
-2, +2, and then 0.
0. Okay? All right, so see if you can figure out, so you can either add to the phase line that you did in practice 1, or you can do a whole new one for the second derivative now. So I just put the second derivative on top of the first derivative that I did in the last practice problem, okay? So don't let this confuse you. We did this already. So, but I've got the -2, 0, and 2 up here on the second derivative line. All right, so to the left of -2 is the second derivative positive or negative, Tobias?
I got positive.
Oh, okay. Let's see. So what's a number to the left of -2?
-5.
All right, -5. So if you want to look at it where it's factored out, like here. So if you plug in -5, 2 times -5 is negative, right? -5 plus 3, -5 plus 2 is negative. -5 minus 2 is negative. So a negative times a negative times a negative is going to be negative. Okay? That makes sense?
Yeah.
Okay. All right. So what about between -2 and 0?
Positive.
That is positive. In between 0 and 2?
Negative.
In between 2 and infinity?
Positive.
Positive. Okay? All right. So do we have points of inflection here? Well, it looks like, go ahead.
Oh, yeah.
Where are they?
-2 and 2.
Yep. How about at 0?
Oh, yeah, 0.
And at 0. So everywhere it changes concavity, you're going to have a point of inflection. Okay? All right. So any questions on that one? Okay, so now, all right, now I want to focus on the graph. What the graph is going to look like at each part. And we're going to use the first and the second derivatives and kind of what you wrote down at the bottom of page 1 to kind of think about what the graph is going to look like. And then this is going to be important for what we do next. Okay? So think about what the shape of the graph is. Okay? All right, so in between -infinity and -2, the first derivative is positive, the second derivative is negative. So if it's positive, that means the graph is going up, but since the second derivative is negative, it's concave down. So it's going to look like that. So that's, the graph is up, but concave down. Does that make sense? Okay. All right, so then this next part between -2 and 0, the first derivative is negative, but the second derivative is positive. So what will that look like? This means it's going up or down?
Down.
And concave?
Up.
Up. Okay, so going down, but concave up. Okay? Now, if you're finding that you're having a hard time visualizing this, okay, you might actually draw this out on your paper and then just even say, okay, this is up, concave, down. Whereas this one is down, but, or maybe we should use, let's not use up and down for the first one. Let's do increasing and decreasing. Okay, so it's the first one is increasing, but concave down. The second one is decreasing, but concave up. All right, this third region between 0 and 2. Okay, this negative for the first derivative is applying to that, so it's still decreasing. But the second derivative is negative, so what does that mean?
Concave down.
Concave down. Okay, so decreasing but concave down, that's what that looks like. So decreasing, concave down. And then the last one, both are positive. So it's increasing and concave up. So that looks like that. All right. So that's going to help us with the next part. Okay. But any questions on that? All right. So what we're going to do now is we're going to talk about so those equilibrium points where the y's are equal to 0, where the makes the derivative equal to 0, they're y values, and so we're going to talk about whether they are stable or unstable from the graph. So if a solution curve, which I'll show you what that looks like, tends steadily toward a value, we say that it is a stable equilibrium. So on the number line, we had them going like this, where they were both approaching a value. Okay, on the y-axis, though, it looks like this. You'll have solution curves that will approach a value from above and below, like that. That's what a stable one looks like. Okay, now on the number line, on the phase line, an unstable equilibrium. So the solution curve tends steadily away from a value. So on a number line, the unstable ones look like that, where they're going away from it. So when we draw them on the y-axis, the graph will go away from the value, like that. And that's when we know it's unstable. So we kind of did it before on a number line, but now we're actually going to be doing it along the y-axis. Okay? Okay, so let's see how that looks. All right, so in this example, see I've got, so this curve right here is going away from the solution y equals 2. And it's going away down here, away from y equals 2. So y equals 2 is unstable. Now here it's concave down and switches to concave up. So that's actually a point of inflection right here. Point of inflection. All right, now these are kind of lousy drawings. Let's get rid of these. Whoops. Okay, so but if I had these solutions and they were going towards this value, then and from above and below, then that's a stable equilibrium point. Okay, so drawing them out like this, so it's a little bit different than on the number line. What you're doing is drawing with the y equals the horizontal lines where your solutions were, your autonomous solutions. And then you calculate, all right, what's happening in each region. So you look at your sign charts. Is it concave up and increasing? Concave down? What's going on? And so then you draw the solutions for each y value and then decide if it's stable or unstable. All right, so see if you can do that for practice 3. So again, we're using the same problem that we did in practice 2. Okay, so this is what I got. Okay, so basically I'm looking at the sign chart. Okay, back over here. And so the first area, so we said the first from -2, from negative infinity to -2 was increasing concave down. So you make this bottom part increasing concave down. So then the next part, you've got decreasing concave up. So that's from -2 to 0. So from -2 to 0, it's decreasing concave up. And then the next region was decreasing concave down. And then we have increasing concave up. So then where the solutions split, then that's unstable. Then here where this curve changes concavity, this is going to be a point of inflection. And then where these two curves come together, then that's a stable equilibrium point. Okay. So how'd we do? Am I going too fast? Did you get it? Kind of? Okay. So let's do another one. So this practice. Okay. So when we're doing the second derivative, this again is a reminder before, sometimes it's easier to multiply than derive so that you don't have to use the product rule. All right. So let's say we wanted to do this. Okay. Now, so you can do the first derivative sign chart just from this. Okay. But when you go to take the second derivative, you might want to FOIL this out and then take the derivative. Okay? But remember, anytime you take the derivative of y, you're going to have dy dx. Okay? So if we FOIL this out, then what would be the second derivative? Jada, what would be the derivative of this?
Would it be 2y dy dx minus dy dx?
So, right. And then the derivative of -2 would just be 0. So now, this person that did this, instead of using dy dx, used y prime, but it's the same thing. Okay? Then what you want to do is actually, so that you can substitute what y prime is, factor it out. Factor out the y prime or the dy dx, and then you'll have 2y minus 1. Then you substitute in what y prime is. So y prime is y plus 1, y minus 2. Okay, so to do the phase lines, to draw the solution curves, you need to then do the first derivative test, say where it's plus and minus, and do the second derivative test. Then figure out where is it concave up and down, where is it increasing and decreasing. So if we run out of time here, I want you to finish this problem before class on Monday. All right, so we've only got 1 minute to go. So again, let's just finish this up for Monday. You guys have a great weekend. And anybody gonna do anything fun?
I'm going to the valley for something my dad hasn't told me yet, but he said it's going to be fun.
Well, it sounds good. Maybe you'll get Diamondback tickets or something, right?
Maybe.
That would be sweet. All right, well, Jada, I hope you have a good weekend too.
You too. Thanks, Mr. Strong.